Hello, my name is Grace Lamb and I'm in Physics 2211 and this is my first lab video, lab number 1, constant velocity. So the purpose of this lab experiment is to observe an object that is traveling at a constant velocity and to use the momentum principle to compare it to a computer-generated model of this constant motion. By analyzing this comparison, the validity of the momentum principle can be proven. The assumptions in this lab is that there is a flat surface with no friction or any other resistance forces, and the object is traveling in a straight line. For this lab, the system is a moving object and the surroundings is everything else. The first fundamental principle behind this lab is Newton's first law of motion, which states that an object in rest or in motion will remain in rest or in motion unless acted upon by an outside force. The second fundamental principle is the Newton's second law, or the momentum principle, which states that a change in the motion of an object is directly proportional to the magnitude of any of the forces applied. This is displayed with the equation on the screen as the net force is equal to the change in momentum over the change in time. By applying these fundamental principles, you're able to come up with a momentum and velocity update formula, which directly translates the fact that F net is equal to delta P over delta T to that the final velocity is equal to the initial velocity plus F net over M delta T. And in this case, because there is no net force, this makes it so that the final velocity is equal to the initial velocity. Then you're able to use the position update formula to further show that the final position is going to be equal to the initial position plus the final velocity times delta t. And in this case, the final velocity is going to be equal to the initial velocity. Once I understood the applications of these fundamental principles, I began with the procedure of this lab. The first step was to record a constant motion of an object along a flat surface with a meter strip along the path to calibrate it. Then I imported a video into Tracker to analyze the video in order to extract the object's position and times. Then I used the momentum principle and other fundamental principles to manipulate the glow strip starter code to correctly portray the motion. And then I compared these two graphs that was given by the observed and predicted motion. In this video, the observed motion is shown to show that the bottle moved as a constant velocity across the flat surface. Then on the right, you're able to see exactly what was manually inputted into Tracker and able to see each time step, which was able to directly come up with the position versus time graph from the Tracker application. Once all this was done within Tracker, I was able to import all the information and create a position versus time plot of the observed motion in the Tracker. From this, I was able to find an initial position, a final position, and a time, as well as a change in time between each of the measurements. After finding all of these values, I was able to manipulate the computational model starter code in order to create a computational model that would correctly reflect the motion of this observed motion. To start updating this code, I used the velocity update formula that was found earlier to say that the initial velocity is equal to the final velocity, which therefore means that the initial velocity is equal to average velocity. Then I took the initial position, the final position, and the change in time from the Tracker, and I was able to find that what the initial velocity was, which allowed me to import both the initial position and the initial velocity into the code. Then I took the delta t that was found from the change in each of the measurements from the Tracker, and I was able to put that in here to ensure that there was the same amount of plot points for the change in time in between the computational model and the observed motion. Next, I continue to use the velocity update formula that showed that the final velocity equaled the initial velocity in order to update the position update formula in order to say that the final position is going to be equal to the initial position plus the final velocity times the change in time. Then from this, I was able to update the object's position in order to just make it so that it was the vector of the ball plus the vector changing at that initial velocity times the delta t. Then I left the vector for the change in velocity the exact same because there is no change in velocity because the force is 0, making it so that this object is moving at a constant velocity. Once I inputted this code, it outputted the image that is shown above, as well as a position versus time graph and a velocity versus time graph. In the position versus time graph, you can see that it is completely linear, which translates to the velocity time graph, which is completely constant. Then I was able to take all of the data and put it into a position versus time graph in Google Sheets, which was able to plot the linear position versus time graph. Then when I put the observed versus predicted motion on the exact same graph, they showed to have the exact same linear position versus time graph, showing that the momentum principle did prove in the computational model that it's the exact same as the observed motion, which I physically observed. Lastly, what does this all mean? So the data wouldn't necessarily change if the x-axis was flipped, it would just make the slope negative. And even though the computational model says that the F net is equal to 0, that doesn't necessarily mean that it actually is, and it makes it impossible to determine how many forces were combined to create this F net equals 0. This is mainly because the computational model does not really account for errors such as air resistance, gravity, friction, and other things like on level surfaces, so it's really unable to be determined if the net force is actually negative. And that's it. Thank you so much for listening to my lab video.